Welcome to This Explainer. Today, we're diving into the invisible, microscopic architect that secretly dictates the physical properties of our everyday world. So, let's start with a totally everyday mystery that most of us probably never even question. Why do ice cubes float at the top of your glass instead of sinking right to the bottom? It's something we literally see all the time, but the physics behind it? Actually pretty rare in the universe. To answer that, we're going to follow this roadmap. We'll start by defining the hydrogen bond, look at how it creates extreme melting and boiling points, uncover the secrets of solubility, check out viscosity and fluid flow, and finally answer exactly why ice floats. All right, section 1, the hydrogen bond defined. First things first, we need to understand the tool that actually builds all these phenomena. Think of a hydrogen bond almost like a highly specific microscopic magnet. It happens when a hydrogen atom, which is already covalently bonded to a highly electronegative atom, develops a partial positive charge. Because of that charge, it gets pulled toward another highly electronegative atom nearby. Usually, that's fluorine, oxygen, or nitrogen. Now, these bonds are weaker than true covalent or ionic bonds, but they are significantly stronger than your standard van der Waals forces. And, there are actually two completely different types of these bonds, and they behave in totally opposite ways. As we can see here, intermolecular bonds, the ones on the left, form between different molecules. They effectively hold different molecules together, which boosts melting points and increases solubility. Classic examples? Water and ammonia. But over on the right, we've got intramolecular bonds. These form within a single molecule. Because the molecule is busy bonding with itself, it kind of ignores its neighbors. That inward focus actually decreases its melting point, boiling point, and solubility. Examples of this are O-nitrophenol and salicylaldehyde. Let's zoom out a bit for section 2, extreme melting and boiling, and see how these bonds drastically alter the physical world. Take water, H2O, and hydrogen sulfide, H2S. Structurally, oxygen and sulfur are in the exact same group on the periodic table. Yet water is a liquid at standard room temperature, while hydrogen sulfide is a gas. Why? Well, intermolecular hydrogen bonds are literally the only reason water molecules stick together tightly enough to form a liquid. H2S lacks these specific strong bonds, so it just floats freely away as a gas. Without this invisible architect, our oceans would literally boil away right into the atmosphere. Absolutely wild to think about. We can see this same thing with p-nitrophenol and O-nitrophenol. They are incredibly similar structurally, but p-nitrophenol has a much higher boiling point. It's because its structure allows for those intermolecular bonds. It grabs onto the molecules around it. On the flip side, O-nitrophenol has a lower boiling point because its intramolecular bonds trap it. It's basically holding its own hands, preventing the molecules from locking onto each other, meaning it takes way less heat to boil away. And this isn't just a fluke. This pattern pops up everywhere. Molecules containing highly electronegative atoms like fluorine, nitrogen, or oxygen always see a spike in boiling point because they form those strong intermolecular bonds. Hydrogen fluoride has a higher boiling point than other halogen acids. Ammonia beats out pH 3 for the exact same reason. And ethanol, it requires way more heat to boil than diethyl ether, all because of its ability to form hydrogen bonds. It is a remarkably consistent rule. Moving right along to section 3, the secrets of solubility. Let's see how this ties into why things dissolve. Ever wonder why a spoonful of sugar just vanishes so easily into your morning coffee? Well, the general rule is that polar molecules like sugars, ammonia, and alcohols tend to be highly soluble in polar solvents like water. But the actual physical mechanism doing the heavy lifting to pull them apart? Yep, that's our invisible architect at work again. If we zoom in on how these substances physically link up, you can see these bonds forming active physical bridges right between the ammonia and the water and the alcohol and the water. The solvent is forming active connections with the solute. That formation of hydrogen bonds is exactly what yanks the substance into the liquid, making it highly soluble. Which brings us to our third big physical consequence in section 4, viscosity and fluid flow. So, what exactly is viscosity? Simply put, it's a fluid's opposition to flow. You can think of it as the internal friction of a liquid. Whenever neighboring portions of a fluid try to slide past one another, viscosity is the resistance they experience. Picture the honey sitting in your pantry right now. Its super thick consistency compared to water isn't just a random trait. Notice that slow, thick pour happening here? That's caused by millions of tiny hydrogen bonds within the liquid actively resisting the movement. They're basically grabbing onto each other, refusing to let go easily as you pour. The more intense the hydrogen bonding, the greater the opposition to flow. And finally, Section 5, Why Ice Floats. Let's solve that mystery from the very beginning. Let's track exactly what happens as water gets cold. In liquid water, hydrogen bonds are constantly forming and breaking. It's this dynamic, chaotic dance that actually allows the molecules to pack relatively close together, giving liquid water a higher density. But as the temperature drops toward freezing, that dynamic dance grinds to a halt. The cold forces those hydrogen bonds into a highly stable, rigid state, eventually snapping the water molecules into a fixed, orderly, crystalline hexagonal lattice. Right at that magical moment of crystallization, this incredibly orderly hexagonal lattice forms. Each water molecule connects with exactly 4 of its neighbors, creating this beautiful, highly specific geometric net. Because this cage-like structure rigidly forces the molecules to spread out at very specific distances, it traps empty space inside the lattice. Think about that. The solid form literally takes up more volume with the exact same number of molecules. It becomes less dense and lighter than its liquid counterpart, and that is exactly why ice floats to the top of your glass. It's pretty mind-blowing, isn't it? If a single, relatively weak molecular interaction has the sheer power to radically alter boiling points, dissolve solid matter, make liquids viscous, and literally allow ice to float so that it shapes the oceans of our planet, what other microscopic interactions are quietly dictating the macro world we live in every single day?